Section 10.5 is on page 611, talks about absolute convergence and the ratio and root tests. So we start with a definition which says a series, a regular series, is absolutely convergent if the series of the absolute value converge, and automatically if the absolute value converge, the actual series converge. So if you want to show whether a series converge or not, and there's a negative in there, meaning I can't use the comparison test, limit comparison test, I can't use the integral test, I can put an absolute value. And if I show that this converge, then automatically I can assume that the original series converge. That's a very good thing to do with negatives, so that I could use those prior tests that I learned. The ratio test. Ratio test and root test are pretty much the same thing as far as conclusion. You're given a series. You take the limit as n approaches infinity of a sub n plus 1 divided by n. And you check. If that limit is less than 1, you say the series is absolutely convergent. Therefore it converges. You don't have to say that. If this number, this limit, is bigger than 1, the original series diverge. Notice there's no absolute value here, only here. And if you get 1, it's inconclusive. The ratio test is used whenever you see an exponential, whenever you see a factorial. If you use the ratio test when one of those two is not present, you will get a 1. You just wasted your time. So those are really useful for exponentials and factorials. Number 1 through 8 says use the ratio test to determine whether the series is absolutely convergent or is it divergent. Well, I'll take on number 2, page 616, the limit as n approaches infinity of a sub n plus 1. Wherever you see an n, you put an n plus 1. Divided by a sub n. And a sub n is literally what you see. So divided by negative 1 to the n, n plus 2 over 3 to the n. That would be the limit as n approaches infinity. Negative 1 to the n times negative 1 to the 1, n plus 3, divided by, that's 3 to the n times 3 to the 1. Keep in mind, a to the n times a to the n is a to the n plus m, and we're going backwards. Instead of dividing, I can multiply by the reciprocal. And you'll notice these cancel out and these cancel out. That's the limit as n approaches infinity of negative 1 n plus 3 over 3 n plus 6. And if I apply L'Hopital lines or divide by the highest power term of the denominator, it doesn't matter. Limit as n approaches infinity, negative 1 you leave alone, that is 1 over 3. So that is 1/3, less than 1. What's your conclusion? Therefore, the series, since there's only one series, the original series is absolutely convergent by the ratio test. So, a bit of work, but you'll get used to it. It's very efficient for exponentials, factorials, or both. So here I see exponentials. Automatically I know I'm going to take the limit as n approaches infinity, a sub n plus 1, 2 to the n plus 1 plus 1 over n plus 1 times 3. If I put an n plus 1 in there minus 1, that's n, divided by 2 to the n plus 1 over n times 3 to the n minus 1. Instead of dividing, I'm going to multiply by the reciprocal. So this is 2 to the n plus 2. divided by n plus 1 times 3 to the n multiplied by n times 3 to the n times 3 to the negative 1 over 2 to the n, 2 to the 1. Maybe I should have did that here, broke that off and said that's times 2 to the 2 squared. That doesn't look pretty. That is the limit as n approaches infinity. And you'll notice this happens all the time. Those cancel out. Those cancel out. I'm left with 2 divides 4 2 times. 3 to the negative 1 moves down. And I'm left with n over n plus 1. So by L'Hopital, that's the limit as n approaches infinity. 2 over 3, 1 over 1. That is 2/3. That is less than 1. Therefore, this series is absolutely convergent by the ratio test. And if I see a factorial and an exponential, then that's definitely, remember the problems back in section 10.3, I said when we get to the ratio test we could do it. We skipped at number 65, I think. Limit as n approaches infinity of n plus 1 divided by 10 to the n plus 1 divided by n factorial divided by 10 to the n. That is the limit as n approaches infinity. Now, n plus 1 factorial, 10 to the n times 10 to the 1, multiplied by 10 to the n over n factorial. Those cancel out. And which is bigger? N plus 1 or n? Since n plus 1 is bigger, I reduce that. So that's n plus 1. The next term is 1 less. That is the limit as n approaches infinity of n plus 1 over 10. That is infinity, which is bigger than 1. Therefore, the original series, and I'm writing that so you wouldn't put absolute value by mistake, the original series diverge by ratio test. You don't have to write the series. I'm just doing that for the next section. Now, we get to this ratio test. I said ratio test twice, didn't I? Okay, let me just give myself a bit more space. Next on the list is the root test. And with the root test states given a series, you take the limit as n approaches infinity of the nth root of the absolute value of a sub n. And the same deal, if it's less than 1, this original series is absolutely convergent. If this limit is bigger than 1, it diverges. And if it's equal to 1, it's inconclusive. And you use this when you could see that I could write this as a series of something raised to the n power, like the following two problems. 9 through 16, let me pick number 10, states, and 14. So use the root test. We're going to use the root test. Again, on a test, I don't specify. You use whatever you want. If I take the limit as n approaches infinity of the nth root, I don't need the absolute value because those are always positive since n is 1 or bigger. So can't I write as 4 over 3 to the n raised to the n? It should be an absolute value, but again, if it's positive, I don't need the absolute value, or you could put it there. Those cancel out, and I'm left with 4 over 3 to the n. That would be a 0 less than 1, therefore absolutely convergent by the root test. Well, ratio test and root test stands for the first letters, so it's all fine to do that. And I'm glancing at this problem, and again, I could look at this problem and think of it as the whole thing raised to the n power, so I could take the limit as n approaches infinity of the nth root of the absolute value of the sine 1 over radical n to the n. That is the limit as n approaches infinity. Those cancel out. Absolute value of the sine of 1 over radical n as n approaches infinity, that's 0. I'm left with the sine of 0, which is 0 less than 1. Therefore, this series is absolutely convergent by the ratio test, or by the root test, I should say. And you get away with it because RT stands for the same 2. And now, I get to the rest of the section, and it says use any method, and that's normally how it is. Notice if I use the root test on this, I'll get into trouble, because if I take this out, the limit is going to equal 1, and that's inconclusive. So, if I take the limit as n approaches infinity of, isn't that 1 minus 2 over n raised to the n? Didn't we agree you could write that as e to the negative 2, no questions asked? Which does not equal to 0. Therefore, this series diverge by test for divergence. When do you use test for divergence? On every problem, every series that you see, you attempt to use test for divergence first if you could. If I glance at this, I do notice that the limit of those will be 0. So here, it will benefit me to use the root test, because that eliminates that n. Absolute value 1 over n minus 1 over n squared. When I say n, I'm talking about this power. That's the limit as n approaches infinity of 1 over n minus 1 over n squared in absolute value. That's a 0, and that's a 0. So this will be a 0 less than 1. Therefore, converge by root test. And that's my conclusion. So I look at a problem, I see a power, or I see an exponential or factorial. I know the root or the ratio will do the trick. Here I see both. I see multiple powers and multiple factorials. So I know this is going to work. I'm going to use the ratio test. A sub n plus 1. I'm going to write this as 2 to the n times 2 to the 1 times n plus 1 plus 1, that's n plus 2 factorial. 3 to the n plus 1 is 3 to the n times 3 to the 1, n plus 1 factorial. Instead of dividing, I'm going to multiply by the reciprocal automatically. That saves me a step. And if you're not comfortable with that, you could write divided and multiply by the reciprocal in the next step. That's not a problem. And here I notice this is n plus 1. This is canceling with this. And this is canceling with this. I'm left with a 2. N plus 2 factorial and n plus 1 factorial. So I'm looking at those two. I notice this is bigger than that. So I could start reducing this. N plus 2. The next will be n plus 1. Once I reach the bottom, I stop. And a 3 there. I'm mapping this with this. This is bigger. So that's n plus 1 times, and I could stop anywhere and slap a factorial at the end, that will work, times n factorial over n plus 1 factorial. Now, if you're thinking, I need a lot of practice, well, lucky for you, we have a lot of homework problems. You can do tons of practice. Do you see that this cancels with this as well? Out of this whole mess, I'm left with the limit as n approaches infinity of the absolute value. The top happens to have a 2 into n plus 2 over 3. Isn't that limit infinity, which is bigger than 1? Therefore, diverge by the ratio test. And that's how it works. It's fairly simple to use, the same over and over. I have 3 more to go. Again, I'm glancing at number 38, and I shouldn't use the root test because factorial is not under a power, so I know the drill. I'm going to use the ratio test. N plus 1 factorial divided by negative n plus 1 raised to the n plus 1. multiplied by the reciprocal of that. That is the limit as n approaches infinity. Whoops. That's the limit as n approaches infinity. And again, this is bigger than that. That's going to happen every time. I start reducing that until I reach the bottom and I stop. Isn't this negative n plus 1 to the n times negative n times negative n to the n over n factorial? This cancel with that. I'm looking at the limit as n approaches infinity, and if I try to combine those, I'm going to combine them that way. Right? And that's going to be and that is the limit as n approaches infinity. If I divide by the highest power term of the denominator, here I'm going to do a nice trick. I don't know how much you're going to like that. I'm going to flip this. And I'm going to say this is, come on again. I'm going to say this is the limit as n approaches infinity. Well, this is 1 over negative 1, which is negative 1. Here, can't I say this is 1 minus 1 over n to the n all raised to the negative 1? Okay, I noticed there's a typo. When I put n plus 1 in there, if I take negative n plus 1 to the n plus 1, doesn't that make that negative n minus 1? Doesn't that make it minus 1? Right? And that's going to make this a negative. And when I break those up, that's going to be a positive. So, isn't this the limit as n approaches infinity? Absolute value of 1 is 1. And isn't this e to the 1 raised to the negative 1? Isn't that 1 over e in absolute value less than 1, therefore absolutely convergent by ratio test? Otherwise it was going to diverge because I was going to get e to the negative 1 raised to the negative 1. 42 would have been a nice problem if the n cubed was raised to the n power. So the ratio test will apply, root test doesn't. Limit as n approaches infinity, again because of this. If this was raised to the 3n, I would have used the nth root. So I'm going to take negative 3 to the n times negative 3 to the 1, n plus 1 cubed, 2 to the n times 2 to the 1, divided, I'm going to multiply by the reciprocal. The reciprocal is n cubed times 2 to the n divided by negative 3 to the n. That is the limit as n approaches infinity. Those cancel out and those cancel out. I'm left with a negative 3 over 2 times n over n plus 1 cubed. Limit as n approaches infinity. Of negative 3 halves, 1 over 1 plus 1 over n cubed, that's a 0. So this is absolute value of negative 3 halves times 1 cubed, which is 3 halves bigger than 1. Therefore, diverge by ratio test. And the last problem is a form of factorial. I want to discuss what that means. If you choose n to be 3, then this is 1, you put a 3 there. you'll get 2 times 3, which is 6, minus 1 is 5. So that's 5 times 3 times 1. That's what that means. And the denominator, if you let n equal 3, the 2 times 3, that's 6. So that's 2 times 4 times 6. This, we know what that is. If I say n equal 4, put a 4 in there. That will be 8 minus 1 is 7. So that's 1 times 3 times, and you go up until you reach 7. If you put a 4 there, that's 8. So you start with 2, 4, 6, and 8. Of course, times 3 cubed plus 1, 3 to the 4th plus 1. So do you notice the next term is always the previous term plus 1 more, just whatever that is. Now I'm going to take that problem and do it on the bottom. So if I take the limit as n approaches infinity, and this is a form of factorial and exponential, so a sub n plus 1 is literally what you see. That's always true in factorial, times if you put an n plus 1 in there. And the denominator will be 2 times 4 times 2n times the next term, which is if you put an n plus 1 in there, times 3 to the n plus 1 plus 1. And I'm going to divide that, so I'm going to multiply by the reciprocal. A bit lengthy. But this is called binomial expansion, something we need in the second half of this chapter. And literally what you see. The beauty of factorials, you could see that all of these cancel out one shot. And all of these cancel out one shot. I'm left with the limit as n approaches infinity. If I distribute that in, that's 2n plus 2 minus 1 is plus 1. This is 2n plus 2 times 3 to the n plus 1 plus 1, and multiplied by 3 to the n plus 1. So, limit as n approaches infinity. For this piece, I'll divide by the highest power term of the denominator. And for this piece, I would write, let me think how I'm going to do this. Yeah, I guess I'll use L'Hopital on that. So, if I continue this right here, this will be 0, this will be 0. I'll be looking at 2 over 2, which is a 1. And 3 to the n plus 1 over 3 to the n plus 1 plus 1. I forgot. So now by L'Hopital, because that's infinity over infinity, this is a 1. That's the limit as n approaches infinity. That will be 3 to the n times natural log of 3 over 3 to the n plus 1 times natural log of 3. That is the limit as n approaches infinity, 3 to the n over 3 to the n times 3 to the 1. Those cancel out. I'm left with 1 over 3, which is less than 1. Therefore, this series is absolutely convergent by the ratio test. And there's our homework, and that concludes this section.